after around 3:30 in the library. Yeah. I did the quiz there. Just like, like, what were the questions?
Yeah.
Just like write out
If you want to write out.
yeah, I'm doing like a walkthrough. What is a rocket?
Yeah.
That's what it is. A lot of it is drawings.
Okay. Yeah. So in terms of like what format the project should be, like taking your question, like general sort of response. So the question was, can I just have a handwritten, like this is my work of like how I approach this problem? And that's fine. Usually there's stuff that you had to assume, or like in the case of a rocket, like how big was the rocket? Like why that big? Is that the size of a typical payload? Is it, are you just making up an example of like, imagine I had a rocket that is made of a squirrel and a bottle, like then that's fine. But usually there's some stuff that you might want to reference somehow of like, this is where this information came from. So that would be the only part that I would suggest also adding.
For example, I have an astronaut. Yeah, I just took the mass of Apollo 11, which is the first rocket that landed on the moon.
Yeah, that's perfect. So, yep, yeah. So as long as like the things that you're kind of building into, because there's always, no matter what you do, there's always assumptions baked in, and that's okay. And a lot of times you can kind of say like, this is a good assumption because I looked it up, and that's like how engineers kind of get around saying like these are all made up numbers. It's like, well, they're representative numbers because we have a body of knowledge of like success and failure over the history of rocket science or 4-bar linkage design, thermodynamics. We have all sorts of things that we can kind of go back and look at. Yeah, thanks for asking. So handwritten is totally fine. Yeah, and then you can scan it same way like as homework.
Today the draft is due, right?
Yeah, today the draft is due. On Monday I had handed out like note cards and said, here, just sketch something. That's totally fine to like take a picture of that and send that in as like, this is my draft. And if you didn't have that, and we also had the Project 1 proposal from Module 1, you could go back and revisit that and turn that in again with like what your new sort of plan is. So the rough draft is literally, it's as rough as it needs to be right now, and that's going to look different for everybody. But it's just to give you like, yeah, you got to do something, like get something, some kind of idea out into the world. Like this, I think this is going to work. This is interesting. Yeah. Cool. Easy enough. Thanks. Started off with questions. More questions? Or coming up soon? Yeah.
Is there also going to be like a final exam, or is this just sort of in place of the final exam?
This is in place of a final exam. And like we've been doing projects, we've been doing quizzes the whole time. Like you've already demonstrated that you applied the knowledge that we were trying to gain. This is your chance to say, this is important to me because fill in the blank, like rockets are cool, or I'm going to become the first person to ever design a spinning top, or I'm going to be the first person to design a Beyblade that is unstoppable, and I will be the king of the 3rd grade all over again. Or maybe hand it down to your child as you become an adult. Like you will become an unstoppable elementary schooler with this Beyblade that is unstoppable. Or maybe, was that middle school Beyblades? I don't know. Elementary, right? Yeah, all right, that's what I thought. It seemed like elementary school. Yeah. Yeah, and what you'll find, like, you're trying to apply things that you already know. You're going to learn something new along the way. It's just the way things go. It's like when you try to build something, you learn. But it's not, you're not meant to like go and do a huge research project into like Lagrangian mechanics or like variational calculus or something. We have some good tools. We've been doing some good work so far. Cool. So then today is our last class to work together. Friday is demo day for seniors. So if you're around and you want to come check out like what senior year is going to be like, I think from 1 till 3 is open to everybody. You can come check it out. I'll be there kind of all day for demo day. And there's a lot of stuff that's exactly like this, and that's kind of why I do this project. One is like, I want you to be able to talk about this class in an intelligible way, like have something that it's connected to. But another part is like, senior design is just 8 months of doing this over and over. Define a problem, solve it, tell us why it's important. Okay, define the next problem, solve it, tell us why it's important. Cool. Other questions? All right. Let me check in. I know I talked to some people last class about like general approaches and questions. So if there's anybody that's like looking for help or you don't know where to go, just like flag me down and I'll try to get to you first. Good plan? Okay.
Oh, okay. Yeah. Yeah.
I see them pretty heavy, but either way, I think there's a 0.
Momentum conserved. Yeah.
So, like, this is a good starting point on. I'm just trying to think about like the 4 bar if it's down and it's sauce or I don't know how you explore.
Okay. Plus 0, right? And no external input supply. Yeah. And that equals. And you're saying this thing is moving this way. This thing is moving. Fall. But total momentum is not 0.
Right, they have different, they each have a method like one, like opposite, right?
Yeah.
So, so impulse is changing.
But see how this one's moving to the left, that one's moving up and to the right. Where's the up? Yeah, the cannon's gotta have something pushing it down, right? Where's that? I think you're right. I think if I took the cannon and fired it straight up, this thing will have no momentum. All it does is push on the floor. So you'll either blast it to the floor or at least in order for the cannon to not be able to move up and down, there's got to be some impulse from the floor. It's the vertical component of our cannonball. Yeah, and it's always conserved, right? But it's conserved in the fact that if you apply force, you're going to change it. You have to set that delta T from the floor, shakes the whole floor. Yeah. Well, I think in this case it would make sense to do like that impulse. We're talking about like what was NV before, what are the forces times time. It really is kind of like the force over a small time. And then what happens after? Yeah, that sounds good. Yeah, I don't know how big a cannonball is. I think they're probably doing like 60 meters per second. Is that 100 miles an hour? Yeah. Yeah, I mean, and you could look up like what is a typical cannonball speed if you want to get like background. Yeah, whatever number you plug in there, the map is still the same. And then yes, I did. And then explain that. Yeah.
I have one nice like explanation part one,
Yeah.
so this would be what I would say my draft and for the final insert like that like more than the regions and this.
Yeah, that would be fine. Yeah. And if you had, like, if you want to submit like a work in progress, then that's fine too. It's just like, I want to make sure there's something done by today, so it's not like next week. Don't worry, I'll start it. I want something. Yeah. What do you want to work on? Okay. Like, do you have like hobbies or career like goals or anything for any? Jetpack. All right. You love a good jetpack. All right. So some standard questions for a jetpack would be like how much thrust do you need to hover? So we can figure that out, right? Like free body diagram. If A is 0, then thrust is mg. Like, okay, that's my steady state. So the packs motions that you have to be able to. I need at least as much thrust as my weight. Next part is like, how fast do you want to go? And how fast do you want to get to that speed? So if you want to fly the jetpack at like, I don't know, 10 or 20 miles an hour, then that's, is it 5 to 10 meters per second? That sounds right. Something like that. So let's say 10 meters per second is your max speed. Then your max kinetic energy, 1/2 mv squared, then u plus the rocket pack. So that gives you like total work that the rocket pack has to be able to do. And then the power is going to be based on how quickly you want to get there. So if you want to go 0 to 10 in a tenth of a second, now you're talking at least your, or sorry, 10 times whatever your work is. So let's say it cost 1,000 joules to get that fast. You need 10,000 watts of power, so they rocket propel. Now we give you like all the design parameters. Like if I had a rocket pack and we design it out where I want, these are the things that I need to get me moving, hovering, those kind of things.
Yeah.
Yeah.
Okay. So what do you mean by simplified tank? What do you mean by that?
Like in this case, we didn't consider
So
stable, where all the linear thrust can go through a center of mass. The reality of a rocket pack is that it's really hard to use because it's like an inverted pendulum problem. You ever held a baseball bat upside down? Yeah. That's riding a rocket pack, that's what you're doing. It's like balancing this thing. So just assuming, at least for the getting baseline work done, if we can align forces in the way that we want, it's not like we can what we want to happen. Yeah. Does that help?
yeah.
Alright, okay.
No, I'm just from like audit, so I'm not sure about everything, just like scientifically makes sense.
Okay.
So, remember I was showing you the equation for work done by graph?
Yeah.
So part one is how much, part one, part two, so part one is how much of this is
Yeah.
I got this equation, what I would want is and it's basically constant, so this is the answer.
Yeah.
That seems fine. It's integrating in distance.
So this is like a DH, right?
Yeah, so
Okay.
sorry, that's what it is.
That's okay.
Yeah, from 0 to 10 million views. That seems
Yeah, from surface to that outer atmosphere.
assuming constant stuff. So
Yeah.
and I picked it to be because I just looked up how fast rockets go.
Yeah.
And we use concept of very far apart.
Yeah.
Then part two, it's part question is use our variance, which is and this is like a in order to do this.
Oh, yeah.
Also do this. Also do this. So you ask me which sections change and relative P and mass times Yes. And so you want to find velocity twice speed.
Okay. Yeah.
So that's why you want your final speed to this, and this is your initial speed. So changing the time is mass times
Yeah.
and this is your change. And so
Yeah.
so force of the plus, so that is 55 meters, right? From the jets. And so my question is how long? So it's huge. So I was going to use FT. FT delta T is equal to delta, right?
Yeah. Yeah.
And so that would just correct the delta T, right?
Yeah, exactly.
That's also okay. Logically.
Yep.
Right.
Yeah.
And the F times the T is equal to
That one, oh, F divided by T?
yeah, that's power.
No, F times V is power.
That's times what?
F times V. So if you have a constant force applied for a constant velocity, the power input from that force is F times V. Because like, if you think about it as force times distance is work, force times speed is going to be work per second. So you end up with power. Yep.
Okay, so that's part two. And part three, this is why we're thinking of like, I can look at it but we can work out first.
Yep.
So the question is, so you look at the rocket, so that's why it's at height reach, and from that each question is how much work is the work? So how much work is the jets? Gross times each.
To anticipate all of that, because you want E0 and you land, right?
Yes.
Okay.
So it's almost as well as high that
And then this G is G?
Yeah.
Enter 1.8 or something.
Yeah, I'm just wondering if I'm missing something that I should consider. So I'm not just saying that I have not tried initially, and so the work is equal to change the energy. So the work done by the jets has to be equal to this. You can change the energy to this too. So the work done by the jets has to be equal to. So I would go about finding that with a constant plus for a certain distance.
You could say thrust is constant, or you could just say total work has to be this, right?
Well, I was gonna say like if I had to find, if I'm starting from H, what's like breaking it into this H, what's the force of thrust that I have to have in order for this to reach 0 by the time it gets to H0?
Yeah,
So
that's a good question, because that, even if it's variable, you're defining what the average force has to be.
right. And so that's literally just F times H is equal to this, right?
Yeah.
Okay.
Yeah.
That sounds good. And that would be my result.
And you could, the force is 1 over R, you could potential energy, like for gravity, if you want. Is like G, big G, times big M, universal gravity.
So what is it?
So right now, you're assuming that, radius plus height squared. You're assuming that you're close, that H is really small and you're really close, so this all turns into this MGH, like a first order approximation. If you want, you can add that there is potential energy even when you're far away. Like if H goes to infinity, then there's almost no potential energy. But here, if H goes to infinity, you have infinite potential energy. If you want.
If H goes to, and what's the mean?
Potential.
Well, if H goes to infinity, then isn't that not even 0? Or doesn't the whole thing go to 0?
It goes to 0, yeah. But in your case, if H goes to infinity, and G infinity is infinity.
Should I instead use that?
This one is in terms of like if you're approaching a planet, this is, the work done is going to be based on this, like how much potential energy for universal gravitation you have.
So
It's not going to make a big difference. Yeah, big G is like a universal gravitational constant. Big M is, in this case, mass of the moon. Little m is mass of your rocket.
is the radius of the moon.
Radius of the moon plus height of the moon.
But I would say that if I would do, I could replace this energy with that.
Yep. Yeah. Again, it's not the end of the world to say MG instead.
I'm the first time I saw that it was just in physics.
Yeah. Okay. Yeah. Yeah. Yeah, are you thinking about like its potential and kinetic energy as it's kind of like moving through this? Because it has, it's like a ground. Yeah, it's not like really shallow. It's because it's trying to get all the wavelengths to the center, right? So they're fighting for each other.
I don't think I did online. On the desk, like, it reaches
Yeah, and this one, total kind of T, right, it's gonna be that 1/2 MV squared of like where is it going? And that's gonna be kind of small compared to 1/2 I, like it's moment of inertia. And theta dot squared, or bigger the moment of inertia. So like big metal big blades versus like plastic dinky ones, they'll spin for a lot longer because I is a lot bigger. Yep. Yeah, one could say so it's spinning around this axis. And it's moving at least two-dimensional, kind of moves like left and right. It's like a pendulum. So it's got some kind of like H. So if we just drop it straight down, initially V is 0, but it moves towards the bottom, and now we have the maximum V. Back up that way. Yeah, yeah, that would be great.
It would also be.
Yeah,
Dropping it into one, yes, that's so one, like, was it how we were getting March,
yeah, so like that. So that chord has like all these things in there, and then inside.
So these players, like,
Yeah, exactly. So as gives the chord, let's say, 20 meters per second. This gear has to rotate R theta dot equals 20 meters per second. So the smaller your radius of that gear and the faster you pull this thing, the more this thing's gonna spin. Yeah, so that's gonna define like how much spinning that energy is at. Yeah, so that ripcord, that's why it's got that big tab. The faster you pull it, the faster the thing spins.
Okay, I should be doing these one day.
No, but these are like, that's two, you can kind of say like, okay, in general, a person can only move their hand so fast. Radius is like, yeah.
So I just like, as soon as I,
Mhm.
and then I can see stuff, like I do, like assuming I get an A as well.
If you consider spinning potential energy, kind of.
As long as it will be the energy return, so we'll be,
Yeah.
so. would
Yeah,
that-
like energy is energy, like it's all measured in units, whether you convert it to heat, work, motion, yeah, sound,
So then, this will be like on like the one initial side, so this will be like the initial. The plan be like the kinetic energy where it's the 1/2 energy squared and the 1/2 the polar force.
yeah.
Yeah, dots, the dots. Energy also. Cause like, I don't wanna like do
Yeah, yeah, it's not meant to be like exhaustive.
well, I feel like I'll start with this with you, and then I feel like there's more to that.
Exactly.
And then for like the project itself, am I just like creating like my own like keep it up and then
You can't, so we were talking about before, like you could do a handwritten or like a report, any format that works for your analysis.
oh, so like probably one with
Like if you want to take videos of the buildings running, then that's fine. Yeah.
I mentioned the point I was thinking of the football system before, like tipping an aircraft plane.
Oh, cool.
So I was thinking of using like, the previous project we used as a platform to model it out.
Yeah,
And then
yeah.
just, you take the data and then it's just analyze like, one modification.
Kind of reverse engineering. Okay, yeah, that sounds great.
Alright, thank you.
so this project's due this Friday, so what's happening? Cause there's a final schedule. And that's
There's no final.
there's no final, so it's just there, so then
Yeah.
this project should be due by this Friday.
Yeah, you can always ask. That's fine. No penalties.
Okay, alright, thanks so much.
Yeah.
I was thinking about it, I had her up on it.
Yeah.
The one. Where the results is going to be.
Okay.
So like, the wire, I can't really talk about that, but I don't know how to like model something, I don't know how to focus it in, like what I focus on.
There's so many different components where you and they're all the same but different. So
I'm trying to pull out some breakfast.
you just came by to say like you wanted to look at just the flat mechanism itself is a 4-bar linkage to control.
Yeah.
Like one of the angles is so and there's kind of like big system things of what are the forces that I need to for the flight line. Well, not even like control things, like if I'm going straight and then I want to turn right, what is the force that I need to turn right? And if I need that force, then the only thing that creates that wind pushing against stuff to actually create, I need enough surface area to create that force, or there's kind of, more individual system levels.
Yeah.
Yeah.
Honestly, I punch too straight, I think that's the wrong way too broad.
So if you want to talk about the throttle, like in terms of the dynamics of it, like what does the system need to do? The main questions are like, what's our max thrust? Probably during takeoff, right? What does it take to actually take off? What's our average thrust going to be? For the most part, we're going to fly cruising. And now the last step is like,
So rather than
like if you're talking about thrust, the first step is just like, what are the forces that I need from this mechanism? And then the next step is like, okay, now how do I get there?
And I just have to model.
Yeah.
And I don't really know what I can do.
Yeah.
I know I can.
Yeah. Let air trying to take off. You know, there has to be more of a weight. Maybe speed is constant. You're accelerating.
It doesn't matter which parameter.
That's up to you. Yeah. Okay. Yeah. Yeah. So for the like, are you saying like an actual? That was I'm gonna draw like the simplified engineering version of it. So there's no restriction on where this thing, like it has a range of motion, but there's no restriction on where it can be. Is that right? So like some things that come out of this kind of because this is a 2 degree of freedom like robot arm. Someone that has a prosthesis. So some things that might come up from this, like if I want to go from here to there, how do I, what's my initial angle and what's my final angle? How did theta 2 and theta 2 change? Like, so it's 2 degrees of freedom, but whenever you're doing motion work, you add another constraint. And one of the simpler ones is sort of like, I want to start here, go to here. So now it's similar problem to slider, right? Because I'm going to pick something up, move it down the table, and then throw it there. The straight line. This is 2 degrees, and then if I say that the path, or if I define the path at this point, this So it starts at x1 and goes to x2. It would depend on, it could be, it could go from yeah. I guess really, sorry, I said one street, really we have like two streets because xi is fixed and then y a equals 0, right? So we take kind of like this point and saying it has to go or yeah, the other thing that you can do is kind of what you're saying, like, all right, if this motion is moving in a circle and this one is moving in a circle, where does this one go? Like, what is that? So, like, one example would be if theta 1 and theta 2 are always equal, then this thing moves in a circle. If theta 1 is always like 2 times theta 2, then spiral around forward. Thanks, you too. Yeah, yeah. What were your thoughts on it? Because you were saying like maybe 4 bar thing yeah. Yeah, yeah, okay. Yeah, because when you have like 2 degrees of freedom like that, you have a lot in the range of motion. You can move to a lot more points. That's kind of benefit. But you also need 2 notices, so it's different from like windshield wiper behind. You have multiple motors for every piece of the thing. Yeah, you're welcome.
So I was thinking about, there's an remember its state. I don't know if you remember.
Okay, yeah.
But they sort of work like, they help just they kind of like hold the camera so people can see. Could be maybe sort of arms.
Yeah.
I was thinking if I could model something like that. Because for example, like if we were trying to do for like a factory setting, I get somewhere that have to carry like boxes back and forth, and I tell that they had some sort of rig like this that would like so they didn't have to hold the entire weight. And so I was sort of looking at this, and I think it would be best to model like a 4-bar method. I was looking at
are those 4-bar?
Not sure, but I saw this one that looks sort of like what I was thinking of. Obviously, it's slightly different. I think it might be. I mean, it's mostly like this sort of.
Oh, that one's to give it like vertical positioning.
Yeah.
Oh, okay. I was thinking the Steadicam
Not
supports.
this part, but this is sort of the arm that holds it up.
Yeah, yeah. Okay, now I got you.
You can see, like here, you can see it's sort of like supporting the weight.
Yeah, yeah. Yep.
So, would that be? Okay?
Yeah, yeah, those would be cool.
Like, so sort of thinking like,
you were to flip this upside down, this would sort of be the bicep of the arm.
Yep.
And this would come out and actually hold whatever object, a box, or I don't know, this machinery or something like that.
Yep.
So, and then I could, I guess, model it using either just myself or with the program you set up for the, which project was that? The 4-bar liquid one? Was it like
number 2.
Yeah. Or set up like that. Obviously, you can readjust some stuff and sort of get like what the or like the constraints might actually and stuff. Yeah, think that would be good, or
Yeah, that sounds great.
okay. No, thanks.
Yeah, you're welcome.
And have a good one.
Yeah, you too. Yep, that makes sense. Yeah.
This is the shoulder arm. This is the arm to hand. So it's like just rebar. So my question is, first off, one of the things just on the house, like -5, I would say. So
Yeah.
and because technically this is this one. So I have 52 each, and then next week I have. Well, that's what I was saying. Okay. It's 2 Thursday, and Saturday, and 11, 5, 6. That's like it's about 8 or 9 o'clock. Okay, that's right. So that's what I was doing. Like, give me different values. There were like different graphs. I think. And then this is what I was also looking at.
And he's also making a test
Range of motion. It's like
for, like,
he said
he said that
swing
he's making a test and it's just like taking it out.
7. So, I mean, because sometimes it makes sense to me. I use this one goes like goes this. It's only in last week. This is the reason last week or like this.
Yeah. So if it's doing something like this, a lot of times the axis over here is like 18,000 degrees. That means it's something for like dislocate your shoulder in the swing. I'll just pull that up. You don't know. That's okay. Everybody, one guy.
I was gonna like involve hands in it.
Yeah.
Process, like gradually, if you're not doing it now.
Okay.
And like maybe like investigating how we can like increase the momentum of the turns or something.
Okay.
I was like, hopefully that's like
Walk me through, how are you trying to increase it? Just tell her to spin faster?
no.
Okay.
Maybe the radius of her arms.
Okay, yeah.
But yeah, I don't know where to go from there because I know we have something about conservation of angular momentum. I don't know if
Yeah, so in terms of like the person, spinning around, right? You can say the arms are just one mass. Just halfway out the arm, and then this is like mass of the ballerina. So initially she starts spinning with hands out, comes up onto her toe, and then afterwards kind of brings everything in, right? Yeah, so this one is, this theta dot's gotta increase because we made, yeah, R got smaller, so we have to spin faster. And you could, I mean, there should be some relationship with like R and theta dot.
I did my car suspension.
If you could stretch your arms out to infinity, like you bring yourself to a stop. Yeah. I don't know if that's, if it feels like it's also still too easy, or.
Well, I was just worried if it was like a healthy class.
This, yeah, it's totally, it's definitely like solid application, and like now you have to figure out like what is the moment of inertia of a person. That also, yep, yeah. Okay, yeah. Yeah, yeah, and it's one, you don't have to say the arms are, always mass, you could say like, all right, cool, we have length, and we have this distributed mass, and now it's NL squared over 12. And so as I pull those linkages in, what's happening? Yeah, now you've got like a rotating linkage system, right? Which would be kind of cool. Yeah. Yeah, thanks. Yeah. Is club length nearly holding it like that?
No, just the actual length of the golf club.
So that is an extension of our linkage system.
Yeah, that's a long this is the club. You're holding this. So shoulder, arm, and
And then three. Yeah. Yeah. So it's a little different. And that's okay. Like, we could say. This, and then theta 2 club maintain.
Like, I will be like,
Theta 2
yeah, it's like,
It is. Okay.
like, all the quick copies. But all you have like 7.
Okay. Yeah.
He has like 2 PM and 10. Is that it? Like PNN, PNB, the degree. Like, lots of like timer.
Yeah.
But he has a 2 PM. In Monday,
Yeah, because the reading.
that's it.
But
And then he
that,
has,
but
then
that
what,
point,
like, ending it with
belt
that.
has to follow. It's as if there are teeth.
We get 8 and then
They
back to
can't
back.
slip with that.
Like,
Then you
what
wear
are
it.
you supposed to do? 8 and then another 2.
Belt move. They spin.
Yeah, yeah, okay. Well, 10 and 4, and they don't,
Okay. Yeah.
then I get they have to take up like 5. Cause now I have to count the traffic. No, but I was into,